Hey everyone, this is a short video on what we will be going over for our Lab 3. This lab covers the core portion of the course focused on real-time operating systems. This is the basics of how we will lay out our RTOS and the scheduler that we will use for it. An RTOS consists of a few main things. We have some threads, which are the things that we want to do. So a thread might be a sensor. Another thread might be another sensor. The key component is that we can guarantee, for the most part, that all of the threads will run. So we guarantee that all of the sensors will have some time active, which is good for safety reasons, among other things. We need a schedule to tell the processor which thread to run, and to schedule which thread to do next, which one to switch to, when to not switch to a thread, and then we need some extraneous functions that we will add finer tuned control over the threads, such as our sleep functions and our semaphores, which are called locking primitives. Our first section here is pretty standard. It has the relevant structures that we're going to use for our RTOS, namely a C-struct, which is called a thread control block. This is a doubly linked list structure. We never actually used the doubly linked function using the previous TCP pointer, but we'll have you guys implement it because it is not a hassle. It's over too. And it has a stack pointer for the thread because each thread has its own stack. It has its little own execution space. They share the same memory map, which for the people that have taken advanced systems programming, you know that most threads share the same memory, which is why threads crashing is one of the issues that comes to threads and the difference between multiprocessing spaces. But yeah, those are the main differences with it. A stack is a simple data structure that they push data into, and it will get data that was most recently pushed to it. We recommend looking at the textbook for some of the basic information on this. It is a rather simple thing, and we expect you guys to have some programming experience before having taken this course. The other thing in Part A is setting up a sysdig. So we need to change context. We need to do our thread switch every so often. How often that is dependent on our sysdig, which is based off a timer interrupt every so often. We will set this to 1 millisecond, for example, or if you want to set this to 1 second, it doesn't matter. A context change is changing which thread is running. So we need to change out the register file and load in a new stack, and then point, or not load in a new stack, but point to a new stack that we want to use. We need to make sure we use our pend sv faults here so that we can tell the processor that we want to change which stack we are using. And yeah, that is how our sysdig is going to work. Part B consists of writing our scheduler. This is an important part. We need to add threads, so we will initialize an array, and then we will add some threads to it. We need to use the addresses of the items in the array. This is what we call statically allocated instead of dynamically allocated. There are issues with some of the drivers for heap management on the TivaWare, on top of the fact that the heap is normally implemented on the reverse end of the stack, and the stack is very, very small on these boards, so we don't have access to a heap, to say the least. The add thread will make our threads. We will use it for our initial threads and any threads that we want to use later on. We need to implement our launch functions. Our launch functions and our start functions, which will set up our global interrupts and everything. We want to fill the initial register file maybe with a base stack. Doesn't really matter. If you want to, you can leave it blank for some undetermined behavior. I recommend making use of uartprint, a function for basic debugging to show that the inits have gone through before you start your RTOS. However, once you do start the thread switching, it is more complex to access the UART module, meaning the debugger will definitely be more useful here. Right. Going into starting the RTOS, enabling interrupts must be done after we load the currently running thread's context onto the CPU. Testing the scheduler, we have our init function, so we just assign some counters into everything, rather standard, so that we can test that each of the tasks are working. You may see instances where the UART modules trip up on each other. This is because we don't have our semaphores implemented yet, because we are trying to access shared resources at the same time. Part C is where we introduce a semaphore. A semaphore is like a little charge card of some sort or checkout card that we need to use a resource, our thread will check out the resource, it will make use of the resource, and it will give the card back. Assuming a context switch happens while it is using the resource, the other threads will look to see if the card is available, and it will say, oh, it's not available, so then the thread will sit there and do nothing. This is what we refer to as a spin lock, because it sits there and it spins doing nothing until the resource becomes available. Let's see. Key things for semaphores: we must see if a semaphore is present. Most of the time, people omit a field in their thread control block for a semaphore that is blocking their thread, which is basically which semaphore, the resource the thread is waiting on. Secondly, the other important part is a signal semaphore. This is basically when a thread is done using something, we need to do a little broadcast to the rest of the system that those resources are not available. Please make use of critical sections, as an interrupt during this time may result in a deadlock of some sort. A deadlock is when a resource is not available to anyone, or a thread never gives up the resource. It is common to see these in Lab3 as the RTOS that this implement is unstable in its current state. You will fix these things in Lab4. Let's see. Oftentimes, again, the semaphore will not be released, so we encourage you to mess around with some of the delay times that you use. You must sleep your thread after you are done with the semaphore. It is imperative that you sleep enough that the thread switch is guaranteed after the thread renders the semaphore back is done. Sometimes you can run into a problem where you sample the Nyquist frequency for this, and it ends up switching all the way back around to the current thread and then retakes the semaphore. So it is encouraged to run the code many times, debug frequently, because it will run into many Heisenbugs with this stuff. Let's see. Parts D and E, rather simple. You've done enough sensor interfacing by this point. Write the multi-mod drivers for our buttons and our LEDs. These are basic S2C devices. And then we want to put this all together and assign our different threads different things. Thread 0 will be our accelerometers, x-axis, thread 1 the y-axis, thread 2 will be our optical sensor, and then 3 and 4 will pull buttons 1 and 2, and we will be able to rotate the board around such that when it's on one side and you hit the button, it will sense based off the IMU. If you hit another button, it will sense based off of the optical sensor. You can look at this little YouTube video for a demonstration. The last thing is to check everything end to end. You will call init. You can do init before your multimod, init functions after your init functions. Again, I highly recommend that you do a UART print after you finish this so that you can check that all of your inits are complete. Then you must initialize your semaphores, and then you must launch your RTOS. After you've launched the RTOS, you should just do nothing, because your RTOS will take over the thread execution, and that's it. You will look in the tablet and see how it is done. This lab is very large in scope. We recommend you start early. We highly recommend that you read the relevant textbook sections. They are very, very useful, and some of the answers for how to do certain parts are in there with a few changes maybe. Please come to office hours. We can help you guys in office hours during lab sections for other TAs. However, the TAs will prioritize their own students in their office hours. There will be online office hours most likely as well. We will prioritize the people that are in person. Happy coding and everything. Yeah, good luck.